thanks everyone for joining this seminar to listen on what Perseverance is doing on Mars at the moment. And I am Sandra Siljeström, and I'm a research scientist at RISE Research Institute in Stockholm. But I spend a lot of time working as a Mars 2020 return sample scientist on the Mars 2020 mission. So I will be talking about mostly some of the results of Perseverance, but mostly the samples that Perseverance has collected for Mars sample return. And this work is obviously not all been done by me, so I want to acknowledge the whole Mars, the other return sample scientists, participating scientists on the Mars 2020 team, and also the Mars 2020 team, of course. Okay, so I will stop the video at the moment. So the title of my talk is "Bring Back Samples from Mars and the Search for Life on the Red Planet." So if we go back to basics, what makes Mars so interesting for astrobiology? Well, obviously, it's one of our closest neighbors, so it's kind of the one easiest to explore. It's one of the rocky planets among Earth, so it has many similarities to Earth. If we look at where it sits kind of in the habitable zone around our sun, it's kind of just on the outside or possibly inside, and that the habitable zone has obviously also moved a bit during the time. And there are many indications that Mars was very similar to Earth in the beginning. And this is pretty obvious if you just take images of the surface of Mars. You don't even have to go down to the surface. You can see it from orbit, where we see a lot of features on the Mars surface carved, that seems to be carved by water, and that includes rivers, forming lakes, and also deltas. And if you go down to Earth, like this image on the top bottom right, you can see that if you look closer, you can see that you have rounding that you would have like from flowing water. So obviously there was some amount of liquid water present on the surface of Mars. But this is of course not the case nowadays. So what happened? Well, it seems like Mars lost most of its atmosphere around 3.6 billion years ago. So the current pressure on the Mars surface is only around 1% compared to Earth. Most of that is CO2, and there's also a small amount of methane. How this loss of atmosphere meant basically both a lower pressure at the surface, but also a cooler climate, because you don't have that heating effect by trapping heat of the atmosphere, and that meant it was very hard to sustain liquid water on the surface. And why did it happen? Why did Mars lose its atmosphere? Well, it's still, I think, a bit up in the air, but one of the theories is that the magnetic sphere disappeared, and this kind of decreased the protection against the solar wind, and then the solar wind kind of removed a lot of the atmosphere. And also the size of Mars kind of plays into this, because of course there's less gravity to keep on to that atmosphere compared to Earth. And this is also maybe an explanation why the magnetosphere disappeared. It should be noted that water do still exist on Mars, just not like flowing water as we've seen that carved out those features, but it still exists as ice on the polar caps. You kind of see that on that Mars. You can see, I mean, you can even see that from space. And there's also plenty of water found in the minerals, and there's also possible detections of water still in the subsurface. And so if you look at Mars today, obviously it's basically a desert. You can see here one of the some rover tracks from, I think it's Curiosity, looking back kind of at its desert landscape. So if life formed during this short period of maybe 500 million years since the formation, or when the surface was stable enough and there was water, it's it may be life had a chance to appear, and maybe it's still there. We don't know. It might have retreated into caves or something that is more protected and where there might be still water, but that's pretty speculative. So one thing, though, which is good with Mars, if you're looking, when you're studying Mars, is because of kind of lack of tectonics, plate tectonics, actually, Mars has preserved much more of its oldest records compared to Earth. So there is actually quite a lot of rocks from that interesting period, older than 3.6 billion years, where we might have had water and possible habitable niches for life. And so if you look at, for example, compared on Earth, you actually only find it in very few places, while Mars contains a lot, most of the surface is basically 3.6. And actually, this might not just help us understand Mars, but also what happened on Earth at this very early stages. So if you look at if you compare that great event when Mars had this climate change, when it went from kind of wet to more drier climate, that happened around 3.6. And if you put that on a time scale of the evolution of life on Earth, you can see that it happened fairly early. But obviously, if we believe the records on Earth, there was life already on Earth at that point when this happened. So if Mars kind of followed the same trajectory, we could maybe speculate that life did have a chance to originate on Mars at this point. But we would only, obviously, it wouldn't be very advanced life we're looking for, because advanced life didn't appear till much later on Earth. So obviously, we're looking more of the things to the right than to the left. But if we would find something to the right, I think we would be something like that on Mars. That would be extremely exciting. So what are we looking for in terms of biosignature when we're looking at Mars? So there are these different classes which people typically define and look for. So we have those that we've shown in the previous image, the kind of structures and textures. So that might be more microstructures, like these stromatolactic features, or it could be just single cells. We look for organics because we presume that it's likely that any life on Mars is built up by organics. We might look for types of minerals that only biology makes. We might look for biochemical activities such as gases produced that in quantities or in abundances we wouldn't expect from just geochemical processes. We can also look at stable isotopes to look for kind of where life tend to prioritize those lighter isotopes. And if we see this kind of unusual fractionation that we can't explain in some abiotic way, that could indicate biology. And obviously some other type of chemistry of unusual molecules you wouldn't expect from a abiotic process. However, the problem is often that these are often not just produced by biology, but they might be produced also by biotic processes. So typically you would like to have a combination of several potential biosignatures to prove that life was on Mars. So there are certain components that kind of preserve or degrade biosignatures. So when we're looking, and this is kind of keeping in mind when we're then trying to pick those samples at Jezero Crater. And what are we looking for? Well, we are looking for certain minerals like silicate, carbonate, thiosilicate, and evaporites, because they're known to contain organic matter and also biosignatures on Earth. And it's an advantage if they're fine-grained. We also want to have reducing conditions because oxidizer will destroy, for example, organics. We also, of course, want to have low temperature and pressure after burial. And this is actually often quite, Mars is actually quite good in this respect because there hasn't been much plate tectonics, so we typically don't have that much burial. However, we do have degradation in form of other that are much more prominent on Mars than Earth. For example, we have a lot of oxidizing. We have a quite oxidizing environment, which you can see in that red color on Mars, which oxidizes all those iron compounds. We have a lot of radiation because we don't have any protection from the atmosphere or an ozone layer. And there's some metamorphism that has happened. So basically, we're kind of looking for those preservers when we're looking, as we're kind of trying to pick the best samples. So the problem is, of course, if you have a rover on Mars, you can't send all the best instruments that you have on Earth. The capability cannot be compared. And for many of the biosignatures, this is a problem. For example, many of the morphological features are way too small for us to observe, so our resolution is not very good. And a lot of those structures are always also covered by dust. And even if we try to remove some part of the dust, it might not be perfect. So it's not like observing in your microscope in a thin section. So we're looking at much larger scales. And also these other signatures often kind of, to be able to kind of identify those as biological, you have to kind of understand what the cycling of these different, for example, the carbon cycle and nitrogen cycle, because if you don't know that, you don't actually know the actual background that kind of biosignature is overprinting and be able to understand it. So that's why we're in an important aspect of in the collection here is that you are collecting a sample suit, and the sample suit will give you kind of giving this background, and you can kind of start teasing out those different cycles that you can then be able to kind of recognize that biosignature overprinting that geochemical cycle, because obviously the elements are cycling some way on Mars geochemically, but we want to know what the biogeochemical cycling is. So that's why we want to do more sample return to be able to study these samples in the lab on Earth. So first of all, and the plan for Mars sample return, so this is the current strategy, how to bring it back. So we're kind of up here in the left corner with Perseverance, which is collecting away its samples. So I think we collected 26 samples, so we're on good way. And then at some point there will be a lander that will have a rocket that will be able to launch these samples off the Mars, off the surface of Mars, and that will kind of release this orbiting sample that will be brought by the return sample. I will show a video in the end, which will kind of illustrate this process. And anyway, so in the end, hopefully these samples will be back around 2033 if everything goes well. So what if we do get those samples back? What can we do with those if you compare? Well, on Earth, we can do so much more than what we can do with the rover. So we can do like, first of all, we can do much more sample preparation in forms of, for example, thin sections and different organic extracts to concentrate whatever we're looking for, isotopes, organics, or whatever. And this cannot be done on Mars in the same way. So obviously we can study on it much smaller and much lower concentration. So much smaller details and also much more concentration. And we can kind of have these suits of many different instruments interrogating a very small subset of samples. And to compare is that we do actually have some samples from Mars now, so in far more Martian meteorites. But the problem with these that they don't have, they have an unknown origin on Mars, and they're all igneous rocks. We don't have any sedimentary rocks. And the best preservation typically on the Earth for biosignatures in sedimentary rocks. So that would be the first that we actually get sedimentary rock. And also MSR, as I kind of pointed out, to actually understand kind of those and be able to tell if it's a biosignature or just an abiotic, we need like a suit of samples to be able to build up these elemental cycles, etc. And that's MSR will be able to provide a suite of samples of known origin. Obviously, we will know, we'll have all the context around that Perseverance is collecting. And obviously, the obvious that we can do much more advanced sample preparation and analysis. And another thing is also, this is something we are also not just doing for now or 2033, we're also doing it for future studies. It's a bit like the lunar sample, which has been continuously giving a new information, and this will be the same for these samples, that they will continue as we get advanced analysis techniques and sample preparation. So here's just some open questions that was kind of put in the IMOS report of what we are interested in. So I would say most of the, we don't know much about biosignature on Mars because we don't know if there's life. So here are some of the questions. So we're interested in the type of processes that might preserve those biosignatures and what can be attributed as a biosignature and what are those biosignatures? I mean, also one thing when you're looking for life on Mars, of course, is we don't actually know how that life looks like. It might be very similar and even related to the terrestrial life, but it could also be something different. So they could be using, you know, a different type of DNA or different type of lipids in their membranes. So we don't actually what we're looking for. So it's also kind of a little bit, we're looking in the dark, but I think we will look for patterns that are kind of different what you would expect from biotic process. That's kind of the approach typically if you don't know actually exactly what you're looking for. If you look at the open questions for the organics, here we're very interested in actually knowing the whole inventory and not just the biosignatures. And it's kind of to get that background. What are the suite of organics that any life would have, you know, which it can use, and how is this kind of cycling? What's the carbon cycle? How is this? You know, is it actually available for any life, or was it available? So this is of course both the past and the present. So there's basically a lot of questions both in biosignature and organics for Mars, and if we look at organics, this kind of mentioned this in an earlier slide that we can probably be pretty safe that because Earth and Mars kind of share such a similar origin in terms of planetary formation. It's very likely that it has very similar elemental abundances, for example. So it's very likely organics is the main building blocks of life on Mars also. And we do know a little bit about organic molecules on Mars, because we do know that, for example, there are some organics coming at least from space. That's been kind of based on theoretical calculations. You can kind of calculate how much the surface from Mars actually receives every year. There's also indication from studies in Martian meteorites that we might have abiotic process going on. Abiotic processes, we haven't seen anything convincing. But anyway, this is kind of just to underscore that kind of lack of knowledge we have of the carbon cycle. So there's basically a lot of question marks. So actually, the only thing we actually know about the carbon cycle is that we do know there's some CO2 exchange between CO2 ice and also possibly the carbonates we see on the surface and the atmosphere, but beyond that, it's pretty open still. We have actually already found some organics on Mars in Jezero, in Jezero Crater with the Curiosity rover, which is kind of a twin to Perseverance. So it looks actually very similar. So we do know already from Curiosity that Mars do have habitable environments. So Jezero Craters shows plenty of sign that it was a lake. We identified basically all the elements there that's needed for life. There's also these redox couples that could be used for microbial energy sources. So it's definitely habitable, and we have identified already organic biomarkers. And that was around 50 nanomole that was identified in the mudstone of Jezero Crater in the Shepherd Formation. And what was identified was typically like simple alkanes and also some cyclic compounds and aromatic compounds. But we still haven't found any important molecules for life, such as amino acids or fatty acids. If we assume we if life on Mars has a similar kind of subset, and we don't know actually the origin of these. Are they from space? Are they from biotic production or from biological production? So a lot of unknowns. So if we then move on to Perseverance, so Perseverance landed in Jezero Crater on February 18th, 2021. And here you see Perseverance together with its helicopter Ingenuity in April, just so shortly after landing, basically. I checked the weather, and it's pretty cold, and it's always pretty cold. But and also one of the things that Perseverance did was kind of nice is actually to record some of the first sounds of Mars, which I thought was kind of nice. So see if I can do that. I don't know if it worked. It seems not to work. So. Anyway, so the Perseverance science goals is basically to look for ancient microbial life and to characterize the geology, the astrobiology, and also to collect samples. And there's also a fourth objective, which is preparing for humans, and I'm not going to talk much about that. So the Perseverance, if you look at on Mars, is up here. Near the EAI Planum. I think this is maybe wrong, might have moved a little bit because I think it's a little bit up here. Yeah, it has, you can see it here. So don't take this red square, it seems to have moved. So it's up here near EAI Plantia. And if you go a bit further, you can see here's this impact basin here, which you kind of saw here in the previous one, and you can see Jezero Crater here. And if you go even further, so here you can, if you look even closer, you can see why the big interest in Jezero Crater, because there's plenty of indications in Jezero Crater that it was a former paleolake. So there's very clear inlet channels and also a possible outlet channel. And along one of the inlet channels here, you have this kind of feature that people have interpreted as a delta. And these are both lakes and deltas are obviously habitable environments. So there was a lot of interest of exploring this. And another good thing about deltas is they also accumulate material. And that also includes biosignatures and organic matter, both from locally, so it could be depositing from the lake in itself, but it's also have all that comes in from the watershed outside here that also kind of collects. So it's like this perfect spot of concentrating these the things we're looking for. And there are several different sites that were identified as good sites for possible biosignate preservation within Jezero. So and because in addition to having that delta, it also has this kind of interesting mineralogy. It does have many of those minerals that we were looking for in that preservation. So we have smectite or phyllosilicate, which is a type of phyllosilicate. We have carbonate detections. So these are, of course, very interesting minerals. So some of the kind of areas that were kind of interesting in terms of biosignature preservation is basically here at the delta. So the delta obviously is very interesting, and especially if we can find some very fine-grained rocks. We have the margin here, the lake margin here, which could be lacustrine carbonates, and lacustrine carbonates typically can preserve a lot of interesting biosignatures. So that would also be a very interesting area to explore. There's also a lot of carbonate detection, and that's both inside and outside. And there's also these possible hydrated silica deposits. So there was a lot of interesting sites to explore. So Perseverance payload, so Perseverance has a very capable payload to kind of characterize. So the payload is mostly to kind of characterize those, is to explore and understand, of course, astrobiology and geology, but it's also, of course, to kind of give the information and all the context for the samples. So it contains a lot of several different cameras on the mast and also on the arm. And then we have also these different spectrometer, which is also sitting. So we have SuperCam here on the head, up here on the mast, and then we also have Sherlock, which is a Raman spectrometer, and fluorescence and Raman spectrometer on the arm, and the Pixel, which is a X-ray spectrometer. So it has a very capable payload to take images and also characterize the mineralogy and potential organics contained within the samples. In addition, Perseverance also carries these sample tubes. So it carries 38 sample tubes that can be filled with different rock, regolith, or atmospheric samples. And then it carries 5 witness samples, which is to track basically any contamination that the rover is might be depositing on the sample, basically. So where are we now? So we started here, we landed here in the Octia Butler landing site, and then we drove kind of around here, and then we kind of back looped around here. So we explored these 2 different regions, Mars and Seda, here on the crater floor. So this is kind of the crater floor. So we landed, we took a little detour to kind of explore Seda here, and then we actually drove back to the delta. And here we explored the delta front, and then we drove up on the fan top, and we explored and collected some sample on the fan top. And currently we're here. We started exploring just a couple of months ago. We started exploring this new region called the margin, where we have that marginal carbonates that kind of seems small space. And we're currently sitting here. Now we're actually taking a nap for a month because there's conjunction, so we can't actually communicate with Perseverance. So it's here, we're going to sit here maybe for a month or so. So how do we actually select the samples? Well, we kind of look at what, so we have all those reports that's been written, the IMOS report, where the science community has indicated what type of samples and what are the research questions they want to answer, and then we try to collect samples that kind of can answer those questions. And of course we will not be able to answer all questions, but hopefully we'll pick and it also depends on what we find, which is kind of this Jezero Crater. So depending on what we find in the crater, and then of course there's practical consideration that maybe this is undrillable because it's too hard rock, or it's on an angle that is not cannot be done. So it's also, we always have to think about the safety of the rover, and then we kind of select and then we acquire the samples. And along when we do sample, we always do this kind of standardized set of measurements, and this is typically done during 10 sols. And it's called the stop list. And this is to be able to make sure all samples have basically the same measurements. And it should be noted that the samples are not measured on directly, but we measure on a so-called abrasion patch next to the sample, because we can't sample, the samples are basically cored directly into the sample tube, so we can't actually measure on the samples directly. So we have to measure on the outcrop next to where we core the sample. So that's a small abrasion patch where we kind of polish away the rough surface and also remove the dust. And this is then put into this kind of, it's put into 2 different documents, the sample dossier, or documents, one with 2 different places. One is the sample dossier, which has basically all the raw data for all these measurements and stuff. And that's kind of stored on the NASA Planetary Science System, PDS. And then we also make these kind of summaries, this initial report, to make it easier for people to actually access the information. And this is kind of how it looks like. So this is, I think, the first one from the Rubion sample. Now I'm going to go back and I'm going to talk a little bit about all the different samples we collected. So there's a lot of samples. We collected already 26 samples, including witness tube, regolith sample, atmosphere, and the rock cores. So here's the crater floor, and this is these samples you see here. So they were collected here in Zeta and Maas. And so these are the samples, all of them. So you have kind of here on the left is the abrasion patches. So here's actually, here's actually where you do the measurement, and then you kind of collect the cores here. So you can see, so with each of these cores samples, there were actually 2 cores because we, and I will explain later why that is. And that we also collected this one, alpha, and Hanoi. So that was basically 8 different 4 sample pairs collected from Maas. So two sample pairs from Zeta and 2 from Maas. And Maas and Zeta are 2 different igneous units. So Maas is a olivine cumulate, and Maas is a basaltic andesite. And we collected 2 different pairs. And they both have been altered. So there's, especially Zeta, has been ordered in terms of it has gone through carbonation. So there's some carbonates. There's also a minor amount of phyllosilicates, and both of them has also been affected by sulfates and perchlorates later percolating through them. And you kind of can see here, so actually this one is from Zeta, C here, and the top ones are from Maas. So you can kind of see here, you see the sulfates here and the whitish stuff, and you can actually see that this one, Guillaume, has actually been quite altered. So here you can see how it looks like. Here's the kind of the abrasion patch, and then there was a drilling, so it's kind of covering the abrasion patch. So you can see, so this is where we do the measurement, and we have all that information, and here's the core basically. And we did a second core on this one. So if I look at the astrobiology potential and the return sample scientists on these, so as they do have some alteration minerals, and possibly there was some hydrothermal alteration, they might actually represent an habitable environment. It's maybe not the top priority for the habit in terms of astrobiology, maybe, but the alteration phases might have trapped some biosignatures. And maybe the most important aspect here will actually be you will be able to use this sample for dating. So we will be able to actually constrain when these possibly habitable conditions were in Jezero Crater. So this is also important to get that timing aspect of the habitability and biosignature. And then if we look at, then we moved on to maybe the most interesting in terms of the astrobiology. So we moved here to after a very fast drive here from Traverse here, where we didn't do much observation. We came here to the Delta front, and we collected a number of samples here. So it's here in red. We can see we collected here at 4 different sites. So here we collected 2 double samples at Thornton Gap and at Skinner Ridge here, and then a double sample here was at Wildcat Ridge, and then we had a singleton sample here at which is not actually listed, but it's up here at Glory Pass. And then we also collected a 4th sample set here at Nubarupa, which is here at Amalik. And I'm going to concentrate on the Berry Hollow here and the Uganik, because I think those are the most interesting. So first of all, these samples are the first sedimentary rocks. So these are clearly all sedimentary rocks. So they will actually be the first sedimentary rocks if they're brought back. And what we explored were 2 different parts of the Delta front. So we explored this Hawkbill Gap here, where we collected, for example, this Berry Hollow and these at the Hawkswallow Flat, and then at Lower Rocky Top. And then we also collected here at Cape Nutchak, and I will show you here. So we collected here at Lower Rocky Top, and then at Hawkswallow Flat here. And then we made collections here at Amelik and Uri Pass, and then here at Observation Mountain, we collected actually a regolith sample. So if we look at if I kind of summarize, I'm sorry if it's hard to follow with all the names, we collected 7 samples, or rock cores to be on, it should be rock cores, I think, and these are the names. And these are all sedimentary rocks, and their grain sizes are from mudstone to coarse grained sandstones. And they contain weathered igneous minerals, but also a lot of various alteration minerals, such as sulfates, carbonates, and phyllosilicates. So kind of exactly what we've been looking for in terms of what we want to have in our samples. We also collected 2 regolith samples at Observation Mountain, this Atmo Mountain and Crossfield Lake. So here's Wildcat Ridge, where we did the separation very whole. You can kind of see that. Look at very fine grained, kind of almost silt to, I mean, we can't resolve actually below like silt. So we don't know exactly, but it's below silt sized grains. And then we have this a little bit more coarse grain at Thornton Gap, which has a lot of carbonates. And this one has a lot of phyllosilicates and sulfates. So I think in terms of the most interesting sample from this one is these that we collected at Wildcat Ridge and Hidden Harbors. This is this Rory Pass one. And those were both sulfate-rich mudstones. And what's kind of interesting with those is that they are these very fine-grained. So they're either siltstone, 2 mudstones. They contain all those kind of very interesting minerals. So it's kind of a phyllosilicate mixed with sulfates and also maybe some minor parts carbonates. There's also these interesting diagnetic features. So it's not so obvious here in this abrasion parts of Berry Hollow, which is from Wildcat Ridge, but it's kind of obvious here in this agony. You see a lot of these kind of sulfate veins and fills, which, for example, could potentially have fluid inclusions that could trap biosignatures. And also together, it's also together that they seem to, the whole environment seems to be kind of consistent with that these would deposit in quieter environments, such as a lacustrine or a delta front environment. Makes this very interesting in terms of astrobiology. So if we look at those samples, this was likely an habitable environment, considering it's like this delta fan front. It has a large biosignature preservation potential because of that fine-grained structure in some of the samples, and also presence of those in minerals we're interested in, and also it formed in that quiet environment that promotes preservation. And here's our we also did this regolith sample here, so we kind of sampled this sand dune here, so you can see this is kind of the place where we have the samples. So that was kind of close to some of the other samples. And another thing we also did in this place was to collect some of 2 of the witness plates to have a record of the potential contamination from those, from the rover in association with these samples. And after this, we deposited part of the samples because it was decided that to make sure that Perseverance, if it would happen something with Perseverance, it was important to have this backup. So that's why we did this backup depot construction. So that's why we double sampled some of these samples, because we wanted to make sure that we had the samples from all of the different sampling sites. So up to this point, we double sampled everything except one sample, this Uganik-Kugalek pair, or not a pair. The Kugalek was a singleton, and so here is kind of where we put. So we put it basically on the surface here. So this is a very flat surface, which is good if you want to land a big lander with a rocket on. And you can see here, they are kind of spread out here. And this was kind of the pattern that we put it in. And here, this kind of a close-up of those samples. And then after this, we kind of continued up to the fan top, where we collected another 3 samples, 1 through 3 samples. And these are the ones. So there's Pilot Mountain, Otis Peak, and Melvin. And they are much coarser grained sandstone. So we kind of left that fine grained rocks behind, but they still contain quite a lot of alteration minerals, both quite a lot of carbonates and also some sulfates and maybe some minor amounts of phyllosilicates. But these were probably deposited in a much higher energy system, like a river system. So they might maybe not as interesting in terms of biosignature preservation, but they will be maybe most important in terms of constraining the timing of the delta deposition. So it will be kind of together with those rocks, from the crater floor, we have a constraint on when actually Jezero Crater might have been habitable and might have preserved biosignature. And we can also use these sample potentially for say something about the Mars magnetic field. So finally, we reach where we are now. So we're not finished exploring the margins. We collected 2 samples here. So those 2 samples, the Bills Bay and Lefroy Bay and Pelican Point. So we're here, kind of on the margin. So we're kind of moving towards out towards the crater rim here. And these are, again, now we're finding a little bit more fine-grained sandstones again. They're maybe like fine to medium sized. However, they have quite a lot of interesting minerals in them, including hydrated carbonates and hydrated silica. And they have this very interesting mix. So they seem to have a very good astrobiology potential. And also this might be a lake margin, which again is kind of this quiet environment, which is good for preservation. So this is, I think, also some of the samples together with the data front, which is maybe the most interesting in terms of astrobiology, because again, we're kind of in this more habitable environment, and it's very good. It seems to have a lot of interesting minerals, make sure that seems to be good for preservation, and also this kind of quieter that also kind of enhances preservation. So this is also very interesting. So in terms of now, we kind of sitting here waiting and maybe exploring and do some more. But after we kind of finish here, we're gonna head out. So this is kind of my arrow to the left here, heading out of the crater. And so we're kind of here, if you look at the red arrow here. So we kind of landed here, and then we drove over and then up the delta front over the delta top, and now we're exploring here the margin. You can kind of see even from orbit how different this margin looks towards the delta front, delta fan. And then we're going to drive here along this kind of the inlet channel out, and hopefully we'll get at some point in a couple of months or something, get out here and start exploring kind of the crater rim and outside crater. And these contain some quite different rocks. They contain some of the oldest rocks on Mars. So those will of course be in very important to constrain like the oldest time of Mars, and also, but they do also contain quite a lot of alteration minerals in terms of phyllosilicates and carbonates. So hopefully we'll have these samples back soon. So we are kind of here now. We're collecting those samples with perseverance. Hopefully we'll have that. These will then be launched with this map vehicle, and then this. And I think it's better if I just show the video here, and so you can see for yourself how it's going to work. Hopefully. yeah, so hopefully we'll, as they get back, we hope we can kind of do these things we're imagining in terms of looking at these samples, looking forward to, so you should all start thinking about what you want to look for and what kind of things you want to answer with these questions, with these samples, because the planning is going on now. The preparations for what type of measurements is already kind of in the way with different working groups and such, but input from the community is always needed. So basically the summary of the conclusion here is that Perseverance has collected 26 samples, including 19 rock cores, 2 regolith samples, 1 atmosphere sample, and 3 witness tubes. These samples include igneous sedimentary rocks from the crater floor, the delta fan, and the margin. And if these are returned, these will be the first Martian sedimentary rocks on Earth. And especially the samples from the delta front and the margin are highly astrobiologically relevant, as they formed in habitable environments and a lot of minerals, and also we get kind of the right mineral sizes that can preserve biosignatures. And hopefully these samples will be back 2033. However, the preparation for analysis back on Earth is already ongoing. And hopefully these samples will answer questions about the emergence and evolution of life, both on Mars and also possibly on Earth. Thanks, that's all for me.
Hi, Sandra. This is Pratibha. I have a question.
Hi.
So you mentioned that the final grain samples, they might have more astrobiological potential as compared to the coarser grain samples. Can you give me the reason why is it so?
Well, typically, if you think of, at least for like organic preservation, it tends to because finer grains like clays and such, they have like big surface areas, so they can bind the organic. So it's partly like an accumulation, and also by like binding these organics, they kind of they also protect it. Another thing is often if you have you want to have kind of rapid when you have it to preserve, you want to have a rapid process, so you kind of soon after the sample is so, and typically small finer grain give better minerals, give better in terms of, for example, morphology and such. So there are several different reasons why it's better to have fine grain. So
okay, thank you.
Hey, hi, my name's Aubrey. Thank you for the really good presentation. It was super interesting. I was wondering, what steps did you take to get where you are within research? As
a
aspiring astrobiologist? Yeah.
Career-wise, well, I think I worked with in terms of I mean, to become a return sample scientist, you had to write a proposal. So typically, if you want to join, at least NASA missions, it's a little bit different for ExoMars, but for European. But typically, you would make a proposal, and obviously, it's to work with relevant questions that the team needs, right? So if you have knowledge that I had maybe knowledge about organic preservation, so that's how I wrote my proposal, right? How to this is the knowledge I can bring. So I think the best way is to kind of become an expert in some particular part, and then you can use that for, I don't know what you want to, if you want to join missions, if that's an interest. Yeah, so that's one way. And another one is, of course, you can also get involved with instrument teams. If you're interested in certain, you can, for example, I'm part of ExoMars, and that's more because I applied and asked if I can join the team. And so it's many different ways. I think the most important is the first kind of, but then also look for the opportunities, because sometimes there are these calls for example, there were calls for MMX, which is I think the Japanese sample return mission from the Phobos, for example. So those are open, and they are also interested. They're often open to early career scientists also. So.
Okay, thank you.
Sandra, hello.
Hi, Suzanne.
Great talk. And I might, if this is a left field question, then just let me know and bail out. You've got one of the atmosphere samples here and the 3 witness tubes, and we know that what is at Three Forks is apart. So where is the pair of the atmosphere sample? Is there any plan to take that, and when and where, or is that just up to, we'll do it when we get to it?
I think there's some idea to do it maybe in the very end, like to collect a dedicated, if that is the community. I think that needs to be a push, to be honest. I think there need to be a push from the community in terms of saying this is extremely important to have that sample, because I think there's always this kind of push that maybe there are more people who wants rock sample versus atmosphere sample, and I totally like understand the need. I mean, there's going to be some, I'm pushing for making sure some of the witnesses get back also, because they also have a tendency to deprioritize. So they will have some atmospheres in them too, but I understand the need for another one. So I think it's not currently in the plan, and but I think there's at least like an idea that would be collected kind of in the very end. Is that? But there need to be a real push to promote that we should collect another one, basically. So
yeah, and that's probably something that the community, including
yes,
those who are here, need to know, because to me, as someone who works on volatiles, it is kind of important to have that baseline.
Yes.
Not just to know what Mars looks like today, but also to make a decision on what might have happened in the sample tubes while they were sat on Mars, while they came back. If we don't have that blank.
Yes, I see what you mean, because of course the headspace is going to be different than the whatever, if you have a clean kind of atmosphere sample, and we want to know that. That's a very good argument for collecting that. I agree. Yeah, it's a bit like the witness. We need a witness, so we have that blank against any organics. So
yeah, exactly. And the headspace gases versus the atmosphere will also be a blank for volatile organics and everything.
Yeah, really. Yeah.
But I don't want to hug your discussion. We have a question in the chat now.
Now we have a question. And, Ben, do you want to ask you a question?
Hey. Hi. Wonderful talk, really great. I'm particularly interested in sort of sulfur compounds and geochemical cycling of sulfur compounds, and I was wondering, do you mentioned you had these sulfur rich veins, and presumably that's anhydrite. Do you?
Yeah, those are anhydrite. Yes.
Yeah. Have you detected any other sort of sulfur minerals, maybe pyrite or something like that?
I must say there's been a considerable lack of pyrite, actually, unfortunately. I don't know why, but even in the igneous rocks on the crater floor, there's not much pyrite. There are other sulfate compounds like hydrated magnesium sulfates and hydrated magnesium iron sulfates, but the pyrite, so we haven't. But as far as I know, I don't think I haven't seen any detections at all, actually. So.
Okay, no, that's really interesting. All right, thank you so much.
But the sulfur must be coming from somewhere. So that's a good question. If it was, oxidized pyrite, basically producing like sulfate-rich fluids, right? So.
Yeah, just because in these type of environments or analogs that I look at in the Andes, and very often it could be comprised of sort of basaltic andesite as well. You see these little rhamboids for sulfur, and I don't know. I sort of thought that could be an exciting target if we got sort of isotopic background at some point. But yeah, if there's none been detected, then that puts a stop in that postdoc idea.
Well, you know, we haven't collected it. There might be more. The geology could be different also in outside. It will be like a lot. The lithology will be quite different outside the crater. So hopefully we can. And one idea is, of course, some of that sulfur-rich fluid could come from the watershed outside. So maybe that could also, some of those rocks could contain pyrite. So
fingers crossed. Thank you so much again.